Good evening, everybody. Sorry for this small delay that we had. It was slightly unanticipated. Welcome to the Nobel Talk in Physics organized by the IST Faculty Association. It's my great pleasure to introduce our speaker of the evening, Professor Prajval Shastri, who is going to tell us about black hole discoveries that won the Nobel this year. Professor Shastri's research focuses on the supermassive black holes in our universe and the galaxies where they reside. She was affiliated with the Indian Institute of Astrophysics, Bengaluru, most part of her career. She has spent several years as a researcher at institutions across the world, such as the University of California, Berkeley, Harvard Smithsonian Center for Astrophysics, and the Kavli Institute of Particle Astrophysics and Cosmology. She also served as the president of the Commission on Astrostatistics and Astroinformatics of the International Astronomical Union. She is the current chair of the Gender in Physics Working Group of the Indian Physics Association and a member of the IUPAP Working Group on Women in Physics. She's an enthusiastic proponent of people's science movement and spends a lot of energy in science popularization activities. Prajval, we are delighted to have you here, and thank you for immediately accepting our invitation to deliver this talk. To the audience, please keep your microphones muted and the videos turned off. Please type your questions in the chat box, both in Zoom and in the YouTube live stream. There will be a question and answer session at the end of the talk, and we'll pass the questions to the speaker. We may also have some of this audience an opportunity to talk, ask the questions personally. Over to you, Prajval.
Thank you, and welcome everyone. I'll just try and share my screen. So, as all of you know, the Physics Nobel Prize went to discoveries related to black holes. And just to go over a brief mention of the citation, it went to the Theoretical Foundation for Black Holes and the Supermassive Compact Object at the Galactic Center, which is our Milky Way. So it went to Roger Penrose for the discovery that black holes, just one second. Because of this, okay, can you see it?
Yes, it's fine.
Okay. To Roger Penrose for the discovery that black hole formation is a robust prediction of the general theory of relativity, and to Reinhard Genzel and Andrea Ghez for the discovery of a supermassive black hole in the center of our Milky Way. So let me start with what are black holes. So black holes are chunks of space-time from which even light cannot escape. So space-time, that's just a fancy way of saying space. And why we need to say space-time is because if I, for example, just say that I'm here in the southwest corner of Bengaluru, that is not that's not a complete description. I have to say I'm here in the southwest corner of Bengaluru now, because I may not be here tomorrow. So that just tells us intuitively why space and time are quite closely linked. So black holes are just, you can think of them intuitively as chunks of space from which even light cannot escape. So this word escape gives us a window into an intuitive grasp of what black holes are. So, you know, this is the Earth, and we throw something from somewhere close to the surface of the Earth. We know that if it is too slow, that thing will fall back into the Earth, whether it's a ball or a cannonball or a rocket or whatever. And if it's launched a bit faster, then it will go a bit further, but still fall back to the Earth. But there is a point, there is a speed beyond which, if we launch it, then it actually escapes the gravitational pull of the Earth, and we call that the escape velocity. and the escape velocity at the surface of the Earth is about 11 kilometers per second. Similarly, the escape velocity at the surface of the moon is about 2 kilometers per second. So even though the moon is smaller, it's also much lighter, and therefore it's a lower escape velocity. So this dependence of the escape velocity on both the mass of the object from which we're trying to escape and the size of the object from the surface of which we are trying to escape is ensconced in this formula that you might remember from high school physics, where it says that the escape speed, or the square of the escape speed, increases when you increase the mass, m, and the square of the escape speed goes down as you as you increase the size. So in other words, so r here is the distance from the center of this object we're trying to escape from to where we're trying to escape from. And what happens is, suppose we imagine that we keep the same mass of this object that we're trying to escape from, for example, the Earth, and squeeze it to a much smaller size, then this formula tells us that the escape velocity would increase. And so that is because you have this r there, the distance from the center of the object to where you're throwing things from. And as this thing goes down, when you squeeze an object, the r reduces, and so the escape velocity increases. Now, we know that the velocity of light is about 300,000 kilometers per second. It's a very, very high value for most in our everyday lives. We don't even notice it, but it does have a speed, and that's 300,000 kilometers per second. So suppose we set that to be the escape velocity. Then what happens? Then we substitute the velocity of escape with the velocity of light, and that is a constant. So we get a relationship between this thing that we call r and this thing that we call m. That is a relationship between how big the object from which we're trying to escape is and how heavy it is. So using this formula, it turns out that if we squeeze the Earth right down to the size of a tiny marble, then the escape velocity will actually be the velocity of light, which actually means that even light cannot escape from it. So this was something that was imagined a very long time ago. There are at least two documentations of this, one by John Michell in England in 1783 or so, and another one by Pierre-Simon Laplace in 1796, where they thought about objects that were so massive that even light could not escape from it. They didn't call them black holes, they might have called them dark stars and so on, but this idea was the precursor of what we think of as black holes today. A small digression, I just want to say that sometimes I might use a different unit for how heavy things are, namely the mass of the sun. This is because in astrophysics, the unit of kilogram becomes a little cumbersome because things are so heavy. So we often use the mass of the sun as a unit for mass. And similarly for power, we use the power of the sun, luminosity of the sun, and we call that L sun. So that was just a small digression to explain some of the terms I might use without explaining. So there was this idea of a dark star from which even light could not escape, and then in 1915 Einstein proposed his general theory of relativity, as all of you know. And the same year, within a few months of his proposing this theory, Carl Schwarzschild predicted that the theory predicted black holes. He didn't again call it black hole. He talked about curved space-time around a spherically symmetric, non-rotating mass. But the formula that he derived was exactly the same as the one I showed earlier, which we got by setting the escape velocity from an object to be equal to the velocity of light. In other words, when an object has a certain mass, if it is squeezed to a size that is given by this formula, then it becomes an object from which light cannot escape. Now, it is true that the formula was the same whether it came from this classical Newtonian idea of escape velocity or it came from general relativity. But the general relativistic description we know now is the more accurate one, and there are many non-intuitive consequences which are not obvious from Newtonian physics. And one of them is that any mass will curve space-time. So what does that? So that means that any mass, I mean literally any mass, my mass, your mass, any mass will curve space-time. But in the regular scheme of things, that's almost imperceptible. So we notice that kind of a curvature only for very heavy objects. And indeed, that was actually tested out. So, so what Einstein's theory intuitively predicts is that any mass will curve space-time, which means that while in our everyday experience we expect light to travel along the shortest distances, which is really straight lines, if the space-time itself is curved, then light would not travel along straight lines, but it would in fact travel along curved paths. So this prediction was very famously verified by Arthur Eddington during the 1919 solar eclipse, and that was a very strong support for the general theory of relativity. And as you can imagine, if the mass of the sun could actually bend light to the extent that it was measurable, then a black hole will bend light even more, because it is even more compact than what the sun is. So the correct description of a black hole is that is the general relativistic one. And by the way, if some of you think that general relativity is something really obscure and not part of our everyday experience, that is no longer true, because unless we take into account the effects of general theory of relativity and the curvature of space-time, our GPSs wouldn't work. So I won't elaborate on that, but that is something that you can look up on your own. So now, given this relationship between the size and the mass in order to have a black hole, the question is there a minimum mass? The formula doesn't predict a minimum mass. So are there electron-sized black holes, or are there black holes seen in the laboratory? Well, so far, not. There has been speculation about such black holes, but so far, the only black holes we know of are cosmic. So, in fact, when John Mitchell and Pierre-Simon Laplace thought about what we now call black holes, their imaginings were also cosmic, because presumably they couldn't reconcile with the idea of extremely high densities for small black holes, and therefore they did need to imagine much bigger black holes, which would be not that dense, but would still have the property of not letting light out. So there was this very important work by Oppenheimer and Schneider in 1939, where they showed that clouds of matter could collapse into objects from whose gravitational force, the gravitational force would be evident, but from which no information could come out. In other words, black holes. Now, this wasn't a very readily acceptable idea at the time. There were many questions. Could these objects really be real? Was it just an artifact that matter would collapse this way, and would the matter eventually come out, or could quantum physical effects prevent such a collapse, and so forth. Meanwhile, there were these very strange objects that had shown up in the sky. So this is an example, and this picture shows you two very sharp-looking objects in the center with this sort of cross shape. As we know, the cross shape is an artifact of imaging when you're imaging very, very sharp objects. So typically stars look like this, but there were some of these objects which looked like stars. They looked really sharp, but they didn't at all show a spectrum that was commonly seen for stars. So a spectrum is where you spread the light from this object in order to look very carefully at how the light changes with frequency. And typically stars showed a spectrum like what is shown on the left. So a typical so-called black body spectrum, which you might remember from your college physics, and then bits of the spectrum eaten away by atoms that at frequencies that were characteristics of those atoms. And this is well understood and well explained, but some of these star-like objects showed a very, very different spectrum, which is shown here in the middle, where instead of light being eaten away, there was excess light, in other words, emission lines. Emission lines themselves are not strange. We see them in the laboratory. But these particular emission lines were not recognizable. So typically in the sky, we recognize emission lines as due to this element or that element, whether it's hydrogen or sodium or oxygen and so on, by the frequencies at which they occur. And such lines have been identified a lot in a lot of stars. But in the early 60s, these emission lines presented themselves, which did not seem to match any known lines that were seen in the laboratory. And then it was the intuition of this astrophysicist called Martin Schmidt, who realized that they were in fact identifiable lines, except that they were all heavily shifted to much lower frequencies altogether. And this is called redshift. And by then it was known that there was evidence for the universe to expand, and that galaxies which had stars in them did show such redshifts, but the redshifts implied by these particular objects were extremely high, which meant that they were extremely far. And if you calculated the amount of light they were producing, it turned out that the powers were extremely, extremely large, and no kind of stellar process, such as nuclear fusion and so on, even multiple stars together, with nuclear fusion producing light, could not replicate the kind of light that was seen from these stars. They were called quasars, and there's this little poem that that is attributed to George Gamow, which again describes the mystery that these objects presented. Now, on the one hand, there was Oppenheimer's work, which showed that a cloud of dust, or stars for that matter, could collapse and create a very, very compact object at the horizon of which gravity would be very strong. And on the other hand, there were these strange objects which presented themselves as extremely luminous with power that could not be explained. What was sort of worse was that the light from these objects appeared to change, and the shine appeared to change on very small time scales, like a week. Now, there's a very interesting, simple argument called the light travel time argument, from which one can deduce how big these objects are. So, as I said earlier, the redshift of the objects told us how far they are, and once you know how far they are, you know how powerful they are by seeing the light, the amount of light that they emit. But this argument was an additional one to tell us how big they were. So the argument is like this. So on the, you see in this diagram a gray circle, and let us say that represents an object. And the time axis runs along horizontally. And after some instant of time, let us say this object suddenly brightens. Now, because this object is so far away, uh, the photons that emerge from the object from the front of it, that is front as in the nearest to us, that would reach us first. Those photons would reach us first. And then gradually the photons from behind would reach us, and finally the photons from the back surface of the object would reach us. Now, if this object instantaneously brightened, we would not see it instantaneously brighten, because the photons, the bright photons from the front would reach us first, and the brightened photons from the back would reach us first. So if something varies on some time scale, let's say a week, then it cannot be bigger than the distance that light travels within a week. So what this means is that using the variations or the time scale of the variations, one can actually probe how big something is that is far away and that we cannot see, whose shape we cannot see. So variations in light tells us about the size of the light source, and these strange objects. So this is an example of such. I think I'll skip this because it doesn't tell us that much. But these kinds of strange objects that were called quasars, they also varied on timescales of about a week, and therefore not only were they extraordinarily powerful, but that power came from an extraordinarily small volume. So it turned out that we really needed the kind of objects that Oppenheimer had talked about. Where near the horizon, one could harness gravity to produce the power that appeared to originate from these objects. But there were many questions about Oppenheimer's objects. As I said, could these objects be real? Was it an artifact? Could matter eventually come out? Could quantum physical effects prevent collapse, etc.? And then Roger Penrose had the answer. So without the assumptions of Oppenheimer, which was spherical collapse and so on, he used very rigorous topology and space-time visualizations in order to conclude that things would really collapse into a black hole. And this paved the way for much more rigorous investigations into this idea. So now, before I go further, I just wanted to make a small digression to talk about false color images, because I'll be showing a few. So what do I mean by that? So this is a regular picture of a cat, and this is what the cat would look like if you took a picture in the infrared, because the infrared would tell us how warm the different parts of the cat is. So the nose is cold and the eyes are warm and so on. And that is depicted in this image, but the eyes cannot see infrared. So so this is the infrared picture of the cat, and obviously the eyes cannot see infrared, so these colors are not colors that we can see. So so that's why this is called a false color image, and colors are used to render the intensity of the light rather than the color of the light. So an infrared picture of a cat would show that the nose of the cat is cold and the eyes are warm and so on, and so they are in different colors, and so the colors are arbitrary, and therefore a false color picture makes sense only if it is accompanied by a key like this, which tells us which color is what intensity. And so, for example, this is another rendering of the same image of the cat in infrared, but it has a different key. So as I said, colors are arbitrary. So these are two pictures of galaxy. They're real pictures from the sky, and they are what we call true color pictures. In other words, the red, green, and blue images of these galaxies have been mixed in a way that they are rendered in a way that the eye would normally see them. Here, there is an image of the planet Uranus, and both these are the same data. The one on the left is a true color image, the way the eye would see it, and the one on the right is a false color image, where different colors are used to represent different intensities. So the false colored image is just a rendering technique that astrophysicists use a lot to show images that are taken at non-visual frequencies. So these objects that I call quasars, these mysterious objects which produced a lot of power from a very small volume, which then found a possible solution in harnessing the gravity from black holes, continued to be studied with extremely powerful technologies. And so not only did it turn out that they emitted a huge amount of power from a very small volume which required black holes, they also squirted out jets of plasma, and these jets of plasma reached out not just from their very vicinity but out into the galaxy, and very often beyond the galaxy into intergalactic space. And not only that, some of these jets were launched very clearly at extremely high speeds, namely relativistic speeds, close to the speed of light. These are some examples. So on the top left, you can see a piece of the sky with a galaxy in the middle and several other galaxies around. And superposed on it is an image in sort of pink and white and so on. This is a radio frequency image which shows these jets of plasma, which you can see are extending out of the center of the galaxy into intergalactic space. And the hypothesis is that there is a really, really giant black hole in the center of the galaxy, and matter matter has come very close to this black hole. It is therefore then sucked into it. It spirals in the process. The matter is accelerated to very high temperatures, and that is that matter shines, and therefore we get all this power. But in addition, this matter also is highly ionized. It produces magnetic fields which land up launching these jets of plasma, which are then squirted out into intergalactic space. It was this kind of a giant black hole that was depicted in the movie Interstellar, if some of you have seen that, and that is what I have shown here, both in the top right and in the bottom left. And that is the picture we have as to how these very energetic phenomena are produced. So all of these really, really needed a giant black hole in the centers of these galaxies, but the giant black hole itself was not seen, and even the dynamics around such a black hole that would tell us what the gravitational field is very close to the black hole, even that was not measured. So this was basically circumstantial evidence for the existence of a giant black hole in the middle of these galaxies. And this here is an example at the bottom within the green rectangle, which shows actual movement of this plasma from the center, which is at the top left, outwards into the galaxy. So this animation has been created by real data and taking images of this plasma over a period of time and then putting all that together to create this animation. So there is no other known physical process that can produce all of this except harnessing the gravity in the close vicinity of a black hole. So that was why I alluded to the Sherlock Holmes argument that when you have eliminated the impossible, whatever remains, however improbable, must be the truth. And I mean, the idea of a giant black hole was not particularly acceptable at the time, but there was no other alternative. So now I want to go back to our Milky Way, our own galaxy, our cosmic village. This is a picture of the Milky Way taken from Leh by Dorje Angchuk. And it shows the Milky Way as having dark patches and bright patches. This is another view where you can see the Milky Way almost horizon to horizon. I hope every one of you has seen the Milky Way with your own eyes, and if not, I would urge you to see it as soon as possible. So the Milky Way we know is shaped like a spiral, like those other spiral galaxies that I showed you earlier. This is not a real picture. This is just a diagram, an artist's impression to show us that structure and to show us roughly where the solar system is. So the solar system is not at the center of the Milky Way, but about 25,000 light years away from the center. And the Milky Way, as I said, shows these dark patches because between the stars of the Milky Way, there is matter. So when I say there is matter, it's actually deceptive because between the stars, it's almost a vacuum. It's a better vacuum than most vacuums we know of on Earth. But yet there are particles, and because the scales are so large, there are then a lot of particles when we are looking towards the center of our Milky Way, which is 26,000 light years away. And because of this, some of these particles are dust particles, and they scatter away the light that comes from the stars behind them. And so when there are a lot of dust particles in some parts of the Milky Way, we see those parts as dark. Now, here with the blue circle, I have shown what is actually the center of the Milky Way. And this is in the constellation Sagittarius, which is kind of visible on the slide if you are very familiar with it. Constellations for astrophysicists are just sort of regions in the sky, like the Gangetic Plain or the Deccan Plateau. That's how we think of constellations, which just describe certain regions in the sky. And the blue circle is where the center of the Milky Way is. Now, because of all this dust that is hiding what's behind it, we are not able to peer into the center of the Milky Way with visible light. This is a zoom in of that same area. So, in fact, one needs either radio frequencies or infrared frequencies in order to peer into the center of the Milky Way. So many groups around the world have used infrared telescopes to study various aspects of the sky. And Reinhard Genzel and his group at the Max Planck Institute in Germany in particular was investigating the center of our Milky Way with various telescopes that were available. So they were actually searching for evidence for a giant black hole in the center of the Milky Way. By giant, I mean more than 1 million solar masses heavy. Now, why was this? This was because there were various hints from the motions of stars and from the motion of gas in the central regions of the Milky Way that there might be something really, really heavy in the center, and that might be a giant black hole. The idea that was being used was fairly simple. It's the idea of Keplerian orbits, just like where the orbit that the moon makes around the Earth or the Earth makes around the sun. And these orbits are created because of the gravitational force, in this case of the Earth or of the Sun. And the idea of Keplerian orbits is that there is a relationship between the mass that is driving the orbit and the speed and the distance from the mass that's driving the orbit. And if you know two of these three quantities, you can determine the third. So the hope was that if the speed of things moving in the center of the galaxy could be found, and the distance of those things from the very, very dark center of the galaxy could also be found, then one could infer the mass of whatever it was in the center. And if that mass satisfied the relationship we know for black holes, then we would know that there is a black hole there. Now, the group of Reinhard Genzel were accumulating evidence in favor of there being a giant black hole there. For example, there is this paper in Nature in October 1996, which says observations of stellar proper motions near the galactic center. Proper motion is just a fancy way of saying the movement of something in the sky that can measure by its shifting position in the sky. There's nothing proper or improper about it. It's just a name that astrophysicists somehow use for this, just to distinguish from any motion that is in our line of sight. Because if any movement happens in the line of sight, we cannot measure that by looking.
There's a break again. Rashmi, can you connect? Yeah.
I think she's there. I guess it's just a matter of time. Yeah, she's there. Praju, you're muted. Praju, you're muted.
Can you hear me now?
Yes. Yes.
Yeah, I think I got muted by somebody.
Oh, no.
Okay. Is my screen seen
No.
Not yet.
now?
No, not yet.
Now?
No.
You can be seen.
Okay, I have to share the screen again, I guess.
Okay. It looked like there was a disruption in the internet. That's the way it felt to us. Yeah. Okay. Now it's fine.
We are a little behind. Yeah, you just started here. The nature
Okay.
paper.
So, can you see the screen now?
Yeah.
Yes.
Okay. So, what did you miss? Did you hear the description of this?
Yeah, you are
paper?
talking about the proper motions, and then you started.
Right. So I just was saying that proper motion is a confusing term, but all it means is it is the way we measure movement by shift in positions of things in the sky, as against movement in the line of sight, for which we have to use a different technique. So there was this paper published in 1996 by Reinhard Genzel and his group, which said observations of stellar proper motions near the galactic center. So they're still not saying we found a black hole. But the evidence was accumulating. Then there is this paper again in 1996. The second author is Niranjan Thatte, and I just picked his photograph to accompany Reinhard Genzel just because, well, he has an India connection. He's an IIT Bombay alumnus like me, and a Berkeley alumnus like me, and so on. So this paper says the dark mass concentration in the central parsec of the Milky Way. This still doesn't say black hole, and they conclude that the dark mass is either a compact cluster of small black holes, 10 to 20 solar mass black holes, or a single massive black hole. So the evidence was gathering pretty fast. So in order to look at the center of the Milky Way and actually determine how the stars might move, which is what is important in order to actually firmly conclude that there is a giant black hole there, one has to overcome two obstacles. The first is that visible light cannot be used because of all the dust particles obscuring, so we have to go to other frequencies like infrared and radio and so on. The second is that the atmosphere is turbulent. Our atmosphere is turbulent and it refracts the starlight, and therefore uh, the image of a star, instead of being steady on the detector, keeps dancing around, which is what is shown in this animation. So the animation on the left shows the actual light rays being refracted on some time scale, and on the right is shown the effect of that on an actual image. So instead of there being a single image of a star, where if you take a long exposure, there is this image dances around, and unless one can capture that at a very high, very short time scale, one will get a smeared out or blurred image of the star, and therefore it won't be, it will impact the sharpness of the image. Now, uh, one way to address this is to go out into space outside of the atmosphere, which is what the Hubble Space Telescope did. So this shows you the impact of that. So on the left is an image of this galaxy taken from the Earth, and on the right is the image taken with the Hubble Space Telescope, and you can see how the one on the right is so much sharper. And The other method is to somehow correct for these atmospheric aberrations. So this is showing you the Keck radio telescope, which is what Andrea Ghez used for her investigations. So on the top left, you're seeing a hexagonal shaped mirror, and the telescope is actually made of an array of such mirrors to make one big mirror of roughly 10-meter diameter. So you can see that in the picture on the right, and I have put a blue hexagon overlapping one of the hexagonal segments just to show that the whole mirror is actually composed of these multiple hexagons. And in the so this was the telescope that Andrea Ghez used in starting around 1995 to image the stars at the very center of the Milky Way. Now, she used the infrared camera, which meant that she could peer into the center. She used this very, very large telescope, 10-meter diameter telescope, which means she could collect a lot of photons. So she could see very faint stars, or alternatively, she could see bright stars even by exposing for a very, very short time. So this kind of a technique is known as speckle interferometry. That's just saying that you capture the image at very short time intervals so that you kind of fight the atmospheric turbulence distortions of the image dancing around. And on the left is shown the raw image. And if you look carefully, you can see roughly sort of a Y shape, and four different objects, and actually maybe 5 or 6 different objects in the image, and each not different objects, five or six different splotches, and each splotch has a characteristic pattern. That characteristic pattern is an artifact which is due to this turbulence. And because she had access to this large collecting area and therefore a lot of photons, she could actually offline correct for these artifacts and produce what is shown on the right. So on the right, each of these splotches is a star, as imaged in the infrared. Now, Andrea Ghez and her team took 3 sets of observations in June 1995, in June 1996, and in May 1997. And so they could measure shifts in these stars. And this is what they found. They found that these stars moved. In this plot, this is kind of a plot of the sky, and the positions of the stars in the sky are plotted here. and you can see several bunches of points, 3 points. So each of these three is an image taken in 1995, another one in 1996 and 1997, and you can see that the stars have moved. They've all not moved all in the same way, but the star which is closest to the center of this image, which is marked by as the center, shows the largest movement or the largest shift between 1995 and 1997. And so Andrea Ghez and her team published a paper where they said that the dynamical evidence, independent of the thing, leads us to the conclusion that our galaxy has a black hole of mass about 2.5 million times the mass of our sun. So the dynamical evidence means that they have measured how much these stars shifted, and they can get the speed from that because they know the dates and therefore the time. And they also know how far these are from that central point because they are able to take sharp enough images that they can see how far they are from the central point, that is the putative center of the galaxy. So this was the landmark discovery. As time went on, the Keck telescope technologically advanced, and there was the technology called adaptive optics, which was installed on this telescope. What this means is that because the mirror of the telescope is segmented and each mirror can be controlled independently, using let's say a laser beam to imitate a star as a reference, they are able to actually measure the atmospheric turbulence and correct for it. So the correction has to happen in a very short time scale, and the correction happens by these actuators that are at the back of each of these hexagonal segments of the mirror. And by correcting for this movement, they can indeed get extremely sharp images, which is illustrated here by this image of the planet Uranus with its rings. So on the bottom left is an image taken with the Keck telescope with its 10-meter mirror. And the image on the right is taken with the same telescope, but with this technology of adaptive optics turned on, which means that you're correcting each mirror for the atmospheric turbulence distortions using a laser guide or using a very, very bright star in the field of view. And the difference is obvious. So the sharpness of the image is key. And so using this now adaptive optics technology, Andrea Ghez continued her monitoring of the stars in the center of the Milky Way and continued to take these images. So now what I will show you is her data, which have been taken over a very long period of time, starting 1995 but continuing into 2018. And this was regular monitoring of that same area of sky in the infrared. So what this rectangle in the center shows is it is showing you multicolored splotches. Each of these splotches is a star, and that's real data. The stars have been labeled. And then there is a white star-like thing in the center, which is not a real object, but that's just there to mark the position of the center of the field. And what I will show you next, and I hope it works, is an animation which has been created by putting these images taken at different times all together, one after another. So, Rashmi or someone, can you tell me if you
Yeah,
see?
we are able to see.
Okay. So here now what you're seeing, again, the multicolor splotches are real data, the real stars in the infrared. They are labeled, and now you can see the shift in the stars as time goes on, and the time counter is at the top right. And to guide the eye, elliptical orbits have been drawn. So this is the crux of it, that there are all these stars in the center of our Milky Way. They are showing movement with time. These movements are not random. The movements are not in straight lines, but they are in elliptical orbits. And what is more fantastic, each of these elliptical orbits has a focus, and the focus is the same for all the elliptical orbits. That focus is marked by this white star-shaped thing. So I want to repeat that the white star-shaped thing is not real data. It's just there to mark the position, that particular position. And now you know why that particular position, because the elliptical orbits of all these stars have that position as the focus. So clearly there is a very massive object there which is driving all these stars into these Keplerian orbits. From this data, they are able to determine the speeds of these stars, and they are able to determine the size of the orbits. So from that, they can determine the mass. So it turns out that the mass that is driving these, originally I quoted Andrea Gheza's paper where they said it was 2.5 million times the mass of the sun, but once the data accumulated and they got better measurements, now the correct measurement is more like 4 million times the mass of the sun. Now, just that doesn't make it a black hole, of course. I mean, you could have a very massive thing of 4 million solar masses. But the important thing is, if you look carefully at this animation and you look at the stars which are seen coming very, very close to that focus, very, very close to that position which is marked by a star, you see that the star completes its orbit and emerges from that position of closeness to the focus, that is called periastron. So all of these stars emerge unscathed, which means that they are not colliding with this very heavy object of 4 million solar masses. Now that means that one can infer a size, or at least an upper limit on the size of whatever mass is driving these things. So just to recap that, there is a very, very heavy mass at the center of the Milky Way, which is driving all these stars in Keplerian orbits, and that has a mass of 4 million times the mass of our sun. It has a size which is smaller than the closest approach of the closest stars. It is at the focus, at the same focus of all the elliptical orbits of all those stars in the vicinity. So this very, very clear evidence that there is a massive black hole in the center. And so this is the leap, shall we say, from this circumstantial evidence for there being massive, a giant black hole in the center of galaxies, just circumstantial evidence, to actual dynamical evidence. So this is really direct evidence. And the idea is quite simple. The idea is of Keplerian orbits. And we are literally seeing Keplerian orbits of stars around the black hole in the center of the Milky Way. Now, what does this mean for the bigger picture? It means, we know that the Milky Way cannot be something special. The Milky Way is just an ordinary galaxy in the universe. So if the Milky Way has a giant black hole in its center, then other galaxies must have too. This is Andromeda, the nearest large galaxy to us. And here's another galaxy. These are real pictures. And even though these galaxies are too far away for us to have really sharp images of the way the stars move in their centers, we have more indirect evidence that they harbor supermassive black holes. These are all real pictures of galaxies further away than the Andromeda galaxy, and all of them, in fact, every such galaxy that has been looked at harbors, shows evidence for a giant black hole in their center. Not only that, it turns out that bigger the galaxy and more massive the galaxy, more massive the central giant black hole. Now, this is something extremely intriguing, and Laura Ferrarize is one of the physicists who has played a major role in showing us this result. And this was just a schematic, but this is what the real data look like. So bigger the mass of the galaxy, bigger the more massive the central black hole. And this kind of a result cannot happen through gravitational coupling, because the central black hole, even though it is massive, very, very big, it cannot actually influence the stars, all the stars of the galaxy. It's what we call sphere of influence, compared to the size of the galaxy, is extremely small. The sphere of influence is a region around the central giant black hole where the gravitational force due to the black hole is comparable to the gravitational field due to all the stars in the galaxy. And this sphere of influence is extremely small. So it cannot be that there's gravitational coupling between the central giant black hole and the gas around it. And so the only way this kind of a relationship between the mass of the black hole and the stars, the mass of the stars in the galaxy, can be explained is if there is some other kind of interaction. And the way we understand it today is that when matter comes very close to the giant black hole in the center, as I showed you earlier, it gets accelerated and heated up and shines, eventually landing into the central black hole. But before doing that, it heats up a lot of the gas around and interacts with it that way. It spews out these plasma jets, which go into the interstellar space of the galaxy, and that way affect the star formation within the galaxy. So what this means is that the giant black hole in the center of a galaxy comes into center stage. So until this point, when it was not clear that ordinary galaxies like our Milky Way had a giant black hole, the kind of objects that I showed earlier, which showed all these jets and so forth, they were thought of as just weird galaxies. People like me who worked on the physics of these, what we called accreting giant black holes in the centers of galaxies, were sort of pathologists who just studied weird objects. But once it was confirmed that there was a giant black hole in the center of an ordinary galaxy like our Milky Way, which was the result of Andrea Ghez and collaborators and Reinhard Genzel and collaborators, it became clear that the giant black hole, or rather it paved the way to this understanding that the giant black hole in the center of the Milky Way is center stage to the evolution of the galaxy as a whole. Of course, it will be a mistake to not mention the other two fantastic results that have come about in the more recent years, much after the very great advancements of the study of the black hole in the center of the Milky Way. One is the black hole coalescence that has been measured by the Gravitational Observatory, which again is direct evidence for the presence of black holes, and also the measurement of the silhouette of a black hole in a neighboring galaxy, Messier 87, which was done by combining a whole bunch of telescopes that observe the sky at millimeter wave frequencies. And I won't go into the details of this because they are a story, each of them is a story in itself. But these have been subsequent direct evidence for the existence of black holes. So Messier 87 actually showed us the silhouette of a black hole. It actually confirmed all of general relativity predictions of Einstein, which is very, very satisfying and which just adds to the whole story. But it was the actual dynamical evidence for this black hole in our Milky Way that paved the way for all these things. This is just the webpage of the Keck Observatory, and the director of the Keck Observatory, Hilton Lewis, has written an extremely nice opinion piece in Scientific American, which is titled "How Andrea Ghez Won the Nobel for an Experiment Nobody Thought Would Work." He says that with authority because when Andrea Ghez proposed her observations in 1995, Hilton Lewis headed an important component, a technical component of the Keck Observatory, and so was involved in making the adjustments to the technology that Andrea Ghez required in order to make her measurements. A lot has been said about how Andrea Ghez is the fourth woman ever to win the Nobel Prize in Physics. So why is this even something to comment upon? Why is it unusual, so unusual for women to get the Nobel Prize in Physics? Marie Curie got it a long time ago, then Maria Gepetmaya got it, and then it was many, many years before Donna Strickland got it, and now Andrea Ghez has got it. I just wanted to go back into a little bit of history, and this is Laura Bassi. She got a physics PhD in 1678. She was a physics professor in the University of Bologna, and she became the chair of experimental physics in 1776 and held that position until her death. So she wasn't there because the University of Bologna wanted women there. She was there because of her talent and her passion for physics. And it is said that she's the second woman PhD in the world. And the Archbishop of Bologna, who later became the Pope, was apparently her patron and recognized her talent and played a major role in her being at the University of Bologna and doing all her physics work and her teaching and so. So I just wanted to point out that there were women who were doing physics since the 17th century in formal forums like universities, getting PhDs and so on. Maria Sklodowska-Curie got the Nobel Prize in 1903 for her fabulous work with Pierre Curie and Henri Becquerel. And there is no question that her work was fabulous, but she was not admitted into the Science Academy. The Science Academy was apparently seen as an academy for men rather than an academy for all people, and somehow, or I should say somehow, women were not quite people, I don't know which. She got the Nobel Prize in Physics because Pierre Curie was outraged when only he and Henri Becquerel were first awarded the prize, and he voiced that outrage. Of course, she went on to get the second Nobel Prize in chemistry later on. Maria Gepetmaya got the Nobel in Physics in 1963 for her fabulous work conceiving the shell model of the atomic nucleus, but she did not get a proper paid position, not at Johns Hopkins, not at Columbia, not at the University of Chicago, where she was an honorary faculty. She finally got a faculty position at the University of California, San Diego, when she was uh, 50 or so, and one should note that she came into the field with a huge cultural capital of being the daughter of a sixth generation university professor. So, despite all that, she did not, and despite her Nobel Prize winning work, she did not get a proper paid position for a long time. And then there are the women, other women who didn't get Nobel Prizes, who did transformational science. So, for example, there's Henrietta Leavitt, who discovered the relationship between the period of change and the luminosity of stars called Cepheid variables, which played a major role in inferring the expansion of the universe. There was Ruby Payne Scott, who came up with the first step to getting super sharp images at radio frequencies. She brought her unique physics plus engineering training to initiate Fourier synthesis in order to image the sun. And she then was able to investigate the physics of the sun and establish a connection between sunspots and radio bursts, and which was published as a paper in Nature. And she also worked to lay the foundations for sharp imaging at radio frequencies, which we now call aperture synthesis. But Ruby Payne Scott had to keep her marriage secret, because if it was not a secret, she would lose her job. Eventually, the marriage came to light, and she indeed was deprived of a permanent position, even though her salary was preserved. And there was no parental leave policy, so she had to resign her job for a bit when her child was born, and so on. There is a story of Cecilia Payne-Gaposchkin, who used the equations of Meghnad Saha. Meghnad Saha applied quantum physics to the ionization of stars, giving a relationship between the temperature and the spectra of the stars, which was key to interpreting them. And Cecilia Payne-Gaposchkin did indeed interpret them, and she came to the conclusion that stars were actually mostly made of hydrogen and helium. It's maybe important or not so important that her PhD supervisor didn't believe her, and so she had to put in a statement in her PhD thesis that perhaps this result is spurious. The result was later vindicated. There is Lisa Meitner, there is Margaret Burbidge, Vera Rubin, who discovered dark matter, and so on. I mean, the list is enormous. There's the story of Jocelyn Bell that is quite familiar to a lot of people, because she's gone around the world giving talks about her discoveries. She discovered magnetized neutron stars, and this was actually Nobel Prize winning work, except that she did not get it. Her PhD supervisor got it. So I wanted to end this with a couple of quotes. One by Landa Schiebinger, who is a sociologist who studied the question of gender and how it plays out in science. And she says that there is a sense that nature takes its course, that given time, things right themselves. But the history of women in science has been characterized not by that, but by the march, not by a march of progress, but by cycles of advancement and retrenchment. And I also want to quote Megan Duty, who's an astrophysicist and director of the Yale University Center for Astronomy, where she says discrimination isn't a thunderbolt. It isn't an abrupt slap in the face. It's the drumbeat of being underappreciated, feeling uncomfortable, and encountering roadblocks along the path to success. It is very, very clear that the very, very small numbers of women in physics, the very clear axis of gender that raises its head, and also the story that the Nobel Prizes tell you just the fact that there have been so few women who've got the prize, and the fact that there have been so many women who've done transformational science but haven't got the prize, all of this tells us that it is the barriers within the profession which are the biggest barriers to everybody being able to realize their full potential and talent within the profession. And the biggest barrier is the lack of acknowledgement of this. And so I wanted to end with a quote from Laura Ferrarize, who is the physicist who did pioneering work in establishing this relationship between the mass of the giant black hole in the center of galaxies and the galaxies themselves. And she says, the sense of achievement derived from concluding a scientific investigation, from obtaining the data to publishing a paper, pales in comparison to the reward of improving the environment in which others can thrive. I will end with this slide, which I actually composed when giving a talk on black hole physics for National Science Day, 20th of February this year. And when I was telling this story of our advances in understanding the physics of black holes, I just realized that I was telling the story of the discoveries by all of these people. And so they're all on this final slide, including Andrea Ghez, the Nobel laureate. And I will end there. Thank you.
Thank you, Prajval. That was an excellent talk, of a fascinating story of black holes in our universe, and also the story of women researchers, women scientists in our culture. So we move on to the question and answer session now. We have already a few questions typed in the chat box. But I guess we can take a mixed approach. Some of you, if you want to ask questions, you can raise your hand, and but please don't unmute and ask yourself unless I request you to. You can also type them in the chat box. I'll wait for people to raise their hands or type the questions in the chat box. But before, already we have questions. So I'll begin with the question Kurinais asked. He had to leave, so he's not here at the moment, but nevertheless, it's an interesting question. So he was asking, how can true motion of stars about the center be measured when we are only seeing a projection?
Yeah, that's an excellent question. I sidestepped that issue when I was describing the result. Indeed, we only see the movement in projection. So to get a three-dimensional sense of the movement, we need to measure the line of sight motion as well. And that is not impossible. But in this case, there is the whole modeling business involved, because the advantage is that all of the stars are revolving around the same mass. So even though each of the orbit is seen in projection, since all of them are orbiting the same mass, there is a factor of redundance there, and that helps the modeling. But yes, I mean, the reason why there was, there was uncertainty in the mass derived was a lot of that uncertainty is indeed related to this business of it being only in projection.
Thanks, Prajval. I'll also ask this question by Shubham Saha, which was asked in the very beginning. He's asking, is there any explanation why the space-time is curved?
Okay, that is more of a question to a general relativist. The way I understand it, general relativity says that any mass will curve space-time. So the gravitational force that we experience is not on top of this curvature. It is the curvature. And so, in a sense, the curvature of space-time is an alternative way of looking at the gravitational force between two masses that we understand from Newtonian physics. And yeah, I cannot answer the question why would mass curve space-time. It just seems to do so, and all empirical evidence supports that claim,
Okay.
including yeses, as I pointed out.
Okay, maybe I could ask Churchill Dwivedi, who wanted to know about mirrors in the telescope. Churchill, can you probably unmute yourself and ask this yourself?
Yes, good evening, ma'am. Can you hear me?
Yes.
Yes, ma'am. I just wanted to ask why specifically hexagonal mirrors are used as an array in the Keck telescope. Like, why not any other shape? Just hexagonal.
Well, hexagonal is one way to tile a sort of quasi-spherical surface, right? So, I mean, I don't think there's anything sacred about hexagonal. You want a segmented mirror. Uh, I don't know. I don't know the technology enough to tell you whether people have studied, whether hexagonal are better than some other way of tiling. But all segmented mirrors seem to use hexagonal mirrors. You want to distort each of those hexagons in order to not only get the surface shape that you want, but also correct for the little distortions due to the atmosphere. So you have to have some segments. And my guess is that the hexagonal ones are the best to manage that.
Thank you, ma'am.
I'll
Okay.
find out more. That's some homework for me.
Okay.
So thanks for that question.
Okay. I'll move to the question Neeraj Sinha asked on behalf of Satakshi Sinha. She wants to know how far is the closest black hole from Earth?
Oh, I don't remember that number offhand, but another issue that I sidestepped is the issue of stellar mass black holes, what we call stellar mass black holes, which are black holes which are not a million times more heavier than the sun, but just a few times heavier. Now, we know that stellar evolution leads to the stars eventually collapsing. And if the star is more massive than, say, 20 solar masses or something, then by the time it explodes, sheds all its stuff, and collapses into a remnant, that remnant, if it is too heavy to be either a white dwarf or even a neutron star, then it will collapse into a black hole. And there are several such black holes which are known. These black holes are more difficult actually to measure and so on, and they're scattered all over the galaxy. The estimates are that there are about 10 million of them all over the galaxy, and we know specifically of roughly 65, or it might be 68 by now, stellar mass black holes scattered all over the galaxy. So there is a website called Black Cat. So if you Google Black Cat catalog of black holes, you will get to this website, and they have a list of all the stellar mass black holes that are known. And so those are indeed, some of them at least, are closer to us than the giant black hole in the center of the Milky Way. And that catalog will tell you which one is the closest. Sorry, I don't remember it offhand.
Maybe I could ask Arun S, who wants to know about accretion disks, to unmute himself and ask the question.
Yes, ma'am. Thank you. So I assume that by the supermassive size of these black holes, they'll also have a very big accretion disk. So are those imaged in the telescopic data?
Yeah, so the accretion disk itself is too small to, we don't have sharp enough images to actually image them, except in the case of the silhouette of the black hole. So in the silhouette is of the black hole, which I very briefly showed, which was got by the Event Horizon Telescope, and which is a very, very exciting result that has surfaced recently. That silhouette is seen against the shine of the accretion disk. So that is one accretion disk which has been actually imaged, but otherwise we are able to measure the shine from the accretion disk, which mostly happens at X-rays, and ultraviolet also contributes to the visible light and so on, but we haven't been able to image.
Yes,
Okay.
ma'am. Thank you, ma'am.
Okay. I think it's Naveen who is asking about observing the giant black hole at the center of the Milky Way. This came from the IST Faculty Association. Naveen, do you want to ask this?
Is it within the realm of possibility to observe a star being swallowed by this giant black hole? Yeah.
Yes, I mean, it depends on what you mean by observed. So, if you mean, can we see a star which goes flush and then, spirals in? Not quite.
Like that. I mean,
Sorry?
no, you showed those orbits.
Yeah.
So then, if an orbit terminates, that would mean it has.
Yeah, true. So if there was actually a star in the close vicinity, then you would see it, either disappear or its orbit, deflected very strongly or something like that. That has not been seen so far. Although the result that I showed, these orbits being trapped around the giant black hole, they have now a lot of data, because of which they are able to measure general relativistic effects. So I talked about them being Keplerian orbits and inferring the mass of the black hole and so on. But now they have enough data, especially for these stars which are going very close to the central black hole, and they can measure general relativistic effects. But so far there has not been a star which is actually which has been seen to plunge into the black hole, although other giant black holes elsewhere in other galaxies have shown what are known as tidal disruption events, and they are we understand that they do occur when a star approaches the close vicinity of a giant black hole. And if the giant black hole has an accretion disk, then it is complicated, because that accretion disk is shining, and the stars, going splashing in and then eventually plunging into getting disrupted and shining and plunging into the black hole has to be seen against the shine of the accretion disk. But if there is no accretion disk, that is, if it is just a dormant black hole, then these kinds of events would be a very good probe of black holes which are not which don't have an accretion disk, and there are many events catalogued which are understood in that scenario.
Richard, I have a feeling that there is a disturbance of some sort from your end. I could hear some sound. Maybe that's fine. It comes in between. Okay.
Oh, what kind of sound is it? Is it a buzz or a clanging, or
Like something is moving around? Maybe it's not a big interference.
okay?
I think I could not request Asif Mohammed. He wants to know about the KSA star. So maybe I could ask him to unmute and ask the question.
Hello, ma'am.
Yeah, go ahead.
So, have the dynamical evidence that there is something massive in the center? I mean,
Yeah.
so my question is, how do you know it's a single object? We perceive it as a supermassive black. So,
Yeah, so in fact, I don't know if that came through, but one of the papers that I showed, which is a paper by Reinhard Genzel, Niranjan Thatte, and collaborators, this was in 1990, so they did speculate that it could either be a single supermassive black hole or a cluster of smaller black holes. But with the precision that is now there, in this galactic center, in the Milky Way center monitoring data. Such a cluster can be ruled out, because even if you have a cluster of black holes, if they are within a very confined volume, then they are going to coalesce, right? So it's hard to avoid that. So now the data are pretty secure that it is a single supermassive black hole, because I don't know if you remember, but the distances were like really small between the what is called periastron, that is the distance of closest approach, um, and the focus of the elliptical orbit.
So something like a binary is now pretty much ruled out.
A binary black hole, you mean?
Something like cluster. So
Yeah, a cluster of smaller black holes is ruled out. Binary black hole, uh, so a binary black hole would result in some other effects. So the kinematics of these stars is now known quite precisely, and my sense is that if there is a binary supermassive black hole in the center, that would have perceptible or measurable effects on the orbits of the stars, which has not been seen.
so basically our precision is good enough now.
As if maybe, I'm sorry, maybe we could move to, sorry for this, maybe we could move to other questions and then we can back us. So maybe I could request Sandhya to ask a question she had posted before.
My question, that was a very interesting talk. I'm from a chemistry background, but still it was really interesting. My question was, I saw that, that mirrors can capture the images of stars without, much disturbance or less disturbance. I wonder, what is the mechanism or principle behind that, whether it collects more photons or whether what's the...
Yeah, so you need detectors which can operate at a very short time frame. So,
but what about the mirrors?
No, the mirror, it's just that the bigger the mirror, the better. So the point is that, like, for example, the CCDs in our cell phones, they accumulate photons over a time period and then give you an image. So if you even see in your cell phone, if the ambient light is low, or if you take a very short exposure, then you don't get clear images, right? So a lot of telescopes use CCDs, but to do this capturing, the speckle interferometry that I talked about, you need special detectors which have a very low time constant, that they can take images at very short intervals. So therefore, since you can't do long exposures, you need a lot of photons in a short interval. So therefore, you can only observe very bright objects, or you need a very big telescope to collect a lot of photons. So it's that kind of trade-off.
Thank you.
The Keck telescope was a very big telescope, 10-meter diameter, so there were a lot of photons. So they could look at not just the very bright stars, but also less bright stars.
Okay. I have one more question. Naveen was asking about, stars falling into the black holes. How often, stars fall into black holes?
Oh, we don't really know the answer to that, because we can't see that happening very clearly. There isn't, there are a few examples of stars falling into giant black holes in other galaxies, and also in the Milky Way, but not enough for us to get a handle on how often does that happen, and because that will also relate to what is the kind of material available in the close vicinity of the black hole and so forth, and so we don't have a clear answer to that.
Has anyone seen that or captured it so far?
So there are these events in which are known as tidal disruption events, which are understood in this way. But we don't have the sharpness of imaging to actually track and follow a star as it kind of spirals in and plunges into the black hole. So,
Okay, thank you.
Okay, in fact, the target disruption events, there was already a question from a YouTube viewer about tidal disruption events. I think that is already explained now, but he has, it's Gautam from the YouTube view. He's asking also about which instrument is used to determine the event horizon and vicinity or in close proximity in the galaxy.
Sorry, what was the question?
The question is which instrument or method, let me repeat, which method is used or which instrument is used to determine the event horizon in the vicinity or in the close proximity in the galaxy? I'm slightly confused myself.
Okay, I presume he means the giant black hole in the center of the galaxy, which is what I talked about.
Yeah, hopefully, yeah.
Yeah, so I did mention that the Event Horizon Telescope had this result fairly recently where they made this silhouette of the giant black hole in the center of a galaxy called Messier 87. Now, that same telescope has also observed the center of the Milky Way, and we do hope to see some results out of that fairly soon. The complication with the center of the Milky Way is that unlike Messier 87, which is a giant black hole with this accretion disk which is shining and then it's spewing jets and so on, so the contrast between the silhouette, the dark silhouette of the black hole and the surrounding area is quite high because that surrounding part is shining. On the other hand, in the Milky Way, there is no, strong accretion disk. There's not a lot of matter which is spiraling into the central giant black hole, and so the contrast is not that high. And also, things change on a relatively short time scale, even maybe over the length of the observation that one is doing. And so these complications have perhaps made it more difficult to get the result out. But they have observed the center of the Milky Way, and we do hope to hear from them.
Thanks, Prajal. I hope you are fine to take a couple of more questions. Is that okay?
Yeah.
Maybe I could request Sauradeep Roy Choudhury, who has a couple of questions about the origin of supermassive black holes to ask. You can ask Sauradeep.
Thank you, ma'am. Good evening, ma'am. My question was that can supermassive black holes be explained on the basis of collapse of stars like stellar black holes?
Yeah, that's a very, very good question. So I guess there was some hope at some point that it was stars that stellar black holes that coalesced to give bigger and bigger black holes, eventually becoming supermassive black holes. And also, the very, very first stars that form, we expect them to be very, very high mass stars because the metallicity, meaning it was mostly hydrogen and helium, and so stellar evolution predicts that the collapse of gas clouds would lead to very high mass stars. So it was expected that the very first stars which formed would be like maybe 100 solar masses and so on. And then if the chance of coalescence is also higher in early times in the universe, and so they would coalesce and form bigger black holes, and then even bigger, and so on and so forth. But the problem has been that in the recent past, we have been able to detect accreting black holes to very, very early times because they shine very powerfully. And on the basis of, not on the basis of the kind of methods that got the Nobel Prize, where actually the dynamics of stars around the black hole are measured, but just from the power that comes out of the vicinity of these giant black holes. If one estimates how heavy they are, it turns out that they are a billion solar masses and even higher. And as you go to earlier and earlier times in the life of the universe, and you still see these really, really giant black holes, then it creates a problem because there is not enough time between the formation of the first stars, however massive. I mean, you can't, as far as I understand, stellar theory doesn't allow you to have, stellar masses which are, hugely more than a couple of hundred times the mass of our sun. So there is not enough time for them to form and then gradually coalesce and make a billion solar mass sized black hole. So there has been a lot of work on this. Somebody called Priyamvada Natarajan at Yale University has made major contributions, and they talk about so-called direct collapse black holes. That is, in the early stages of the universe, you have these massive gas clouds which directly collapse into 10,000, 100,000 times the mass of the sun-sized black holes, and then then the one can understand how there could be billion solar mass black holes at the beginning of the universe. So this is a very outstanding kind of problem, astrophysical problem currently.
I see. Thank you, ma'am.
Okay, is Samarthi Sharma who had a question? Are you willing to ask this, Samarthi?
Yes, ma'am. So, ma'am, quasars are powerful radio emitting sources, and black holes are supposed to be the power source of quasars. So, I have like two questions. I want to know, is it possible for quasars to be powered by something else and not a black hole? And the second question is, when do black holes exist on their own without a quasar? Like, what are the physical conditions for a black hole with a quasar and for a black hole without a quasar?
Okay, so the first answer is, the Sherlock Holmes argument that even before all this work by Andrea Ghez and so on, where they actually found dynamical evidence for a giant black hole in the center of the Milky Way, it was impossible to explain the power that's coming out of quasars any other way. So in the beginning, it was about explaining, we saw hot gas at very high speeds, and even if it's not a black hole which is driving this hot gas in Keplerian orbits, maybe it could be that there are these very massive hot stars which could drive this gas and give us those kinds of kinematic speeds of the house gas and so on. That was talked about at some point, but whatever you do, you cannot produce these jets of plasma which are squirted out from the center of the galaxy out into intergalactic space. And not just that, many of them are launched at relativistic speeds. Now, there is no known way to create that except using accretion around a supermassive black hole. So that is the answer to the first part of your question. The second question was, as I understand, can you have a black hole without a quasar? Is that what you asked?
Yes, ma'am. Like, when do black holes exist on their own? Like, what are the physical conditions for a black hole to be present on its own and for a black hole to be acting as the power source of a quasar?
Yeah. What I described in the talk is that the Milky Way is an ordinary galaxy. It has a giant black hole, which implies that most galaxies, ordinary galaxies, will have giant black holes. So that is the circumstance. So it is now becoming clear that a giant black hole in the center of galaxies is just regular and ordinary. Not all of them may have material in their close vicinity in order to produce, in order to spiral in, get accelerated, heated, shine, and produce these bipolar plasma jets. So now the idea is that so a quasar really is the more correct term for a quasar really is accreting supermassive black hole. So when the black hole is accreting, which means when there is matter, it may be stars and gas around and so on, in its very close vicinity, then that will inevitably spiral around and plunge into the black hole. You get heated, it will shine, it will become what we call a quasar. If now that material will go on spiraling in, then eventually all that material will be exhausted. So then that giant black hole will stop being a quasar. It will switch off. So the accreting phase is understood now as a phase in the life of every galaxy. And it could be that after a while, again, something triggers and matter rushes towards the center of the galaxy, and then it goes close enough to the central black hole that again it will start to accrete, and then again it will switch on as a quasar or accreting supermassive black hole.
I get it. Thank you, ma'am.
Okay, Sally has a question about lifetime of black holes. Maybe you could ask.
Yeah, madam, my question is: once a black hole is being formed, does it remain forever?
Yeah. So, well, yes and no. There is this prediction by Stephen Hawking called Hawking that, and he said that black holes can give out something called Hawking radiation. This is a theoretical prediction, and what that means is that a black hole will give out this radiation, and then over time it will kind of evaporate. Now there are sorry.
Yeah, that means it has a depth. It has a depth.
Yeah, I mean, it will evaporate. Yeah, you can call it death. But the thing is that this is just a theoretical prediction. There are some problems with the theoretical prediction itself. But other than that, it's not observed empirically. And even the theoretical prediction, the way this radiation arises, it is inversely proportional to the mass. So very, very tiny black holes will give a lot of Hawking radiation and evaporate according to this theory. But massive black holes, the kind of black holes we've talked about, even stellar mass black holes, and certainly giant black holes, supermassive black holes of 1 million solar masses and above, will have a very, very low level of Hawking radiation. And therefore, their so-called evaporation timescales would be extremely large, larger than the life of the universe. So we don't expect, even as per the prediction, we don't expect them to, quote unquote, die or evaporate.
Thanks, Prajval.
Okay, thank you, madam.
Vineet had a question about space-time bending. Maybe Vineet, if you are there, can you ask, unmute and ask it?
Yes, ma'am. Good afternoon, ma'am. Ma'am, actually, what's my question is, ma'am, we know that every object in the universe bends space-time proportional to its mass. Since we can assign mass to each black hole, ma'am, then how can we say that black hole can bend the space-time to an infinite extent? That means what I'm coming to ask is, the black hole also should bend the space-time only to a finite extent, no, ma'am? That's my question.
As far as I know, that infinite thing happens at the singularity, which is inside the black hole. So the event horizon kind of protects us from all that. So you have, so you will have some curvature, and obviously the curvature will increase as you go closer and closer to the event horizon. But beyond the event horizon, we don't see any.
Okay. there is a question Jayanti wanted me to ask on behalf of her. She is asking the trajectories in the animation you have showed. The trajectories has been predicted over taking a few observations over years. Considering the distances, is it hard to believe these observations that they provided with the full trajectories?
So over time, they are mapping more and more of the trajectory. So a couple of them have recently closed. But yeah, I mean, I would expect, because there's a lot still to investigate in terms of, I mean, what was until a few years ago, what they derived were Keplerian orbits and the mass and so on, but now they're getting into the regime of actually testing general relativity and so on. So definitely, I would expect them to continue the monitoring and map out more and more of each of the elliptical orbits. I don't know if that was what the question was.
Yeah, I think it was. Okay. So, is there any? I don't know whether I've missed anything. I think I covered almost everything that was there. If anybody has more questions, please feel free to come up. I guess. Yeah, I think it's almost. All right. I think, yeah, this went into quite a long discussion. And Prajval, particularly the question answer session was also fantastic. And we really had I'm sure that faculty members and students who were actually the majority of audience had a great time asking. We could ask several important, interesting questions. So thank you so much for giving this wonderful talk, and thank you on behalf of the ISD Faculty Association, and also personally from my side.
Well, thank you. Thank you very much for having me, and it was a lot of fun. And some of the questions, I mean, I really enjoyed all the questions. They're really good. Yeah, thank you.